Global Navigation Satellite Systems, or GNSS, make up a major part of the navigation component of CNS ATM, and this will only increase as more ground-based navaids are decommissioned. Satellite navigation systems are used in all forms of aviation, from highly integrated systems in airliners to handheld mobile devices. Most people associate GNSS with GPS, the US government's satellite constellation, but over the years more have come online, including the Russian Gnss, European Galileo and China's Beidou. And more constellations will come online in the future. There's a big difference between aviation and non-aviation receivers. Aviation receivers are certified. Uncertified receivers, including mobile devices, have no way of detecting errors. Unbelievably, they can be out by more than 500 nautical miles, and they do not meet any of the requirements for IFR navigation. So how does it all work? Well, there are three elements to GNSS. Firstly, there's the satellites, and with the US's GPS, there's 30 and 4 spares, and they're traveling in 6 orbital planes about 18,000 kilometers above the Earth. And each one of them has an atomic clock and is transmitting GPS signals. Secondly, there's the GPS receiver, giving the pilot positioning, velocity and precise timing information. This means the satellites transmit data about their current and predicted location, timing and health, and the receivers interpret the information to estimate their location on Earth relative to the satellites. Finally, there's ground-based control, a network of monitoring stations that checks the accuracy of the satellite positions and their atomic clocks. GNSS works out a navigation solution for an aircraft from the differences in the time it takes for the radio waves from the various satellites to reach the receiver. It takes 4 satellites to tell you where you are, but before you go find yourself, you should be aware the system does have errors. Solar radiation and the gravitational pull of the Earth and Moon can cause wobbles in the satellite's orbits. The ionosphere, a layer of charged particles about 200 kilometers from the Earth's surface, can slow the radio signals down, skewing the position and time information. All of these errors tend to amplify or cancel each other out depending on the geometry of the satellites, but they limit GNSS accuracy to about 10 meters. However, the accuracy can be improved by using an augmentation system. Augmentation corrects the errors in the GPS system using a range of technologies. SBAS, or satellite-based augmentation systems, use dedicated high-orbit geostationary satellites to get ranging, integrity and correction information from a GNSS ground monitoring network. Next-generation SBAS that'll ensure accurate positioning and vastly improve the precision of GNSS. There's also GBAS, or ground-based augmentation systems. It's where a ground station is installed at an airport to monitor GPS satellites and transmit corrections, integrity parameters and approach data through a VHF uplink on board the aircraft. GBAS is coming online at major airports around the world. As the capabilities of GNSS grow, there'll be tremendous benefits to civil aviation worldwide, including the opportunity to continue decommissioning costly ground-based navaids and the further enabling of performance-based navigation, PBN, to allow for more efficient use of airspace.